All right. Good afternoon. So I'm going to speak to you, not quite so loudly, about ACT3. This is the self-assembled nanomaterials for energy generation and energy storage. And by and large, this is a new assembly of people. There are a few people on this list have worked pairwise, but this is a new assembly of people. So the people from Penn, our leaders are Chris Murray and Zara Fakrari. I am now partially co-leader because I'm making the presentation today, I guess, and Patrice Renaud from the Giant side. But we anticipate active and profitable and valuable collaborations with Russ and Rob Riegelman and Zhang Feng and Amy. I met Gang this morning this is Bryn Mawr College. Then a whole host of people from Giant and people from Solvay as well as we move forward. Okay, so in the case of a disaster, there's a critical need for energy. And I'm sure we'll understand this more after this afternoon's talk, but in my brief thinking about it, think of the panic you have when your cell phone dies, right? And there's not even a world crisis at that point. Cell phone and communication is critical for identifying and tracking where people are, tracking where supplies are and how soon they're going to get there, keeping track of ongoing weather conditions, as well as the electricity that might be necessary to cook food and to have medical procedures, right? The need for electricity is obvious in the case of a disaster. And the question is there a way that within a shelter, within a tent, we can incorporate energy conversion and energy storage? Okay. So these are the goals of ACT3. So we want to incorporate solar energy conversion. We want to incorporate that system, and we want to incorporate energy storage device into a flexible structure. So this isn't like putting a traditional solar cell onto a shed with a rigid roof. We want it to be part of a flexible shelter to reduce weight, improve transport, and all of that. So those are very ambitious goals. I liked Vijay's comment about the flying car. It's like we're gonna have an energy generating tent. It's kind of the same level of ambition. More precisely, there's a lot of options for how to tackle these, and so we're focusing on two. One is to increase the solar energy conversion by designing a multi-layer system involving polymers and nanocomposites that will be more efficient than your traditional silicon-based solar cell. And this has to do with capturing more of the light that the sun gives us. All right? And it will be important, I'll say more about this later, that these coatings that are designed to capture a wider range of the solar spectrum have to not interfere with the other coatings. It's like going to be 3 active coatings. The active coating associated with water collection and or the active coating associated with antibacterial. So Act 1 and Act 2, we have to make sure our coatings don't nullify those 2 attempts. Really design them in concert. And the second thing then would be after the solar energy is converted into electricity, we need to store that. I mean, we might want to be using the electricity on us when the sun is out, but we're going to want the electricity 24/7. So we need to find a way to store that energy into something that is lightweight and a flexible battery. And so again, this might be part of the tent fabric. But it might also be possible to put this into the tent poles, which again have some flexibility, lighter weight, but that might be another way to integrate this into the entire shelter. Critical partnership, certainly with Giant, with regard to integrating these energy materials and the sort of fabulous expertise and experimental expertise they have in situ and in operando. So I think in situ methods might be a common phrase. It's where you're manipulating the material and characterizing it at the same time, in situ. In operando is when you're actually running a device and characterizing it at the same time. Okay. So the issue in the solar energy is that silicon-based photovoltaics are good for only a portion of the solar spectrum. And so the solar spectrum here is shown in the blue, and the silicon absorption is shown in green. So, it's not doing a great job at low wavelengths, and it's losing the higher wavelengths altogether. So there are a number of strategies for taking in this longer wavelength light, and this is Chris's work. Chris is focusing on taking this bit of energy and trying to convert it into a region where the silicon-based device will be more effective. All right? So it's not designing the conversion from light into electricity. It's about taking the solar spectrum and converting the wavelengths that the sun gives us into the wavelengths of light that we're good at converting. All right. And so that's kind of shown schematically here. So this is a fiber which can be woven into a fabric or canvas for a tent. And it will have the three coatings. The base part of the fiber will be an optical waveguide, which will be designed to transmit light down to the photovoltaic cell. So we're not designing this piece. The focus of the active coating is not to replace the photovoltaic cell, but to design coatings, like I said, to convert a broader wavelength of light. Okay, so to keep the light inside the waveguide, we'll have to have metal on the ends and on the bottom half of the surface. Okay, but for the side of the fiber that faces the sun, Act 1 and Act 2 will focus on this top coating. And then the next two coatings will be these nanoparticle polymer combinations that will convert the wavelengths to improve their properties. Okay. So the approach then, there's a lot of physics in these layers. What materials do you pick for your nanoparticles? What are the shapes of the nanoparticles? How far apart do you put the nanoparticles? And then the stability issues associated with developing those coatings. And so traditionally that luminescent solar concentrator, so this is the idea that I've been explaining about changing the wavelength to get it to the wavelength that's efficient for the photovoltaic cell. It's traditionally been done with dyes. So you have some top layer, the wavelengths that are efficient can get through. Then you have to use multiple layers, right? So you have different dyes that will specifically change one range of wavelengths into another range of wavelengths. Right? So for each band of wavelength that you want to convert, you need a different dye. A more promising method then would be to do the nanoparticle polymer nanocomposite. And so this is an example of work from Chris Murray's group where these nanowires have been put into a plastic, thermoplastic, and you can see that it's changing the wavelength of the light of the so that it can be converted into the photovoltaic. So the overall approach is Chris's expertise is in solution-grown nanoparticles and designing those nanoparticles to have the right efficiencies for the light conversion. And so that's just solution and the different quantum dots. And the point that Chris wanted to make sure I made was the fact that quantum dots are making their way into commercial devices and downshifting for displays and solid state lighting. So this is not so much of a pipe dream. Right? It's already in those applications. It will have to be modified to go into the photovoltaic business, but it seems it's quite viable. It's quite viable. Okay. And the other thing that's important here is, so this is the curve that's a little to the left is the curve for absorption, and then that the particle will absorb. Well, that's the absorption curve as a function of wavelength. and then it will emit at a different wavelength, right? So by tuning the elements that are in the particle and the size and shape of the particle, you can control where it will absorb and where it will luminesce. And it's important that these two peaks are suitably separated, because it's really not going to work if you absorb light and then emit it too close to this original peak, because then it'll just reabsorb, right? So by tuning the details of the nanoparticles, you can get these peaks well separated. So you can absorb, shift, and emit the light. Okay. Zara Fakrari and Chris Murray have a nascent, I would say a nascent collaboration on this. Zara's expertise, among other things, is this spectroscopic ellipsometry. And what this allows Zara to work on is the optical properties of these hierarchical hybrid systems. Right, so it's not enough to just look at these films in transmission. So the optical properties both in plane and through plane, so in plane and through plane, are both important, because that will impact how the light is absorbed and what the luminescence structure is, what the luminescence is. All right, so very elegant characterization. Because it's not just, the study of these particles in dilute solution is not the story, right? Because the way their proximity to one another, their orientation to one another is all important, and you can only capture that in a film, and then you need methods like this to do the characterization. Just starting to build the collaborations with colleagues in Giant, and there are almost too many opportunities. There is a wealth of riches. So there's expertise in controlling interparticle distance by designing the DNA strands that can link particles together. This is very interesting in the sense that by designing the DNA strands, you can precisely control the interparticle distance, right? And that will controls their optical properties and the plasmonic properties. There's the opportunity to do electronic paramagnetic resonance, EPR. This is an important characterization method that's not available to Chris and Zara at the moment, but allows for more detailed analysis of the physics within these systems. And then combining the nanoparticles into polymers, again, is really just a hierarchical polymer nanostructure sort of thing, which can play into the block copolymer regime, looking at structures over a variety of length scales and then how they respond to light. And then the other way to control interparticle distance and interparticle orientation within the film is by using other interesting materials like liquid crystals, surfactants, and these other things, dendrimers that have interesting hierarchical structures. Okay. All right. So that's everything with regard to the energy conversion. So designing these multi-layer coded optical waveguides that are mirrored on the back to drive the light down the fiber, the optical fiber, and multiple layers on the top to get the broadest spectrum of light, solar light, converted by the photovoltaic cell that's like down at the end of the fiber. So I imagine a whole set of little, like there's a tent, and then there's a whole set of photovoltaic cells down low on the tent. And the light hits the fibers and then goes down like that. That's how I envision it. The other advantage of the fibers is, like when people put flat solar panels on their house, there's all of this, math and solar position, sun position, to make sure that your flat solar panels are, in the right orientation to get the most sunlight, right? And in solar fields, there are computers and motors that like tilt the solar panels so that they get as much light as the sun progresses during the day. By using a cylindrical fiber, you're already capturing a lot of different angles of the sun. So you can just put your tent down in any orientation you'd like. Okay. The other half is, as the solar energy has been converting into electricity, you could be charging your cell phone battery or charging up your laptop or whatever else you need to do with the electricity. But let's say, you need it 24/7 when the sun goes down, or if we have a couple cloudy days. So then it's a matter of batteries. And so, okay, this should say electrolyte. I'm sorry. The electrolyte that's in the batteries have to transport ions without transporting electrons. So the electrolyte is the thing between the two electrodes. And in this case, I'm showing the battery discharging. And so over here, there's typically some carbon-based material where lithium is intercalated. And as you discharge the battery, the lithium leaves the carbon material, goes through the electrolyte, and then is intercalated into some metal oxide. Okay, this is fine, with a couple exceptions. This is typically a flammable liquid with the dissolved salts in it. And so it works well in the sense that the lithium ions are well solvated, and because it's a fluid, the lithiums move pretty quickly, right? And so in your laptops, this is the sort of technology you have. And one of the reasons why laptop batteries are as heavy as they are is because you need to have a lot of housing around the flammable liquid. Right? You can Google laptop fire if you like, but that's what happens. Like something happens to the battery, and the flammable liquid escapes and gets hot, and then you catches on fire. Okay. Another issue is to have higher electrical storage density. And a good way to do that is to convert this from a lithium intercalated carbon to lithium metal itself. Now, this has a number of issues because lithium metal is flammable, and then you're putting it next to a flammable liquid, and so bad things have been known to happen. And so particularly because with the lithium being just a metal, when it replates, when you charge up the battery and the lithium moves over to the left, it doesn't replate flat. And over time, there can be asperities which then grow out and make dendrimers and will short out the circuit. So for to facilitate using lithium metal as as the anode and to prevent fires, there are a number of strategies trying to use solid polymer electrolytes to provide not only safer but lighter weight, because you can reduce the amount of protective housing. And you might also be able to make flexible batteries. Now, moving to a solid polymer electrolyte in batteries is a big challenge. It's like flying cars. And by and large, the strategy has been to take a polymer of high dielectric constant and to try and dissolve a salt in it. It's not too different than the liquid electrolyte. You have a high polarity solvent and you dissolve your salt in it. It just hasn't been working very well. But the advantages nonetheless are to move to a less, solid polymer electrolytes will be less flammable, so it will require less packaging. It'll prevent the formation of the dendrites that short out the circuit. And it could be incorporated into fabrics or tent poles. But to date, the conductivity has just been lousy by a couple orders of magnitude. Right? They're just not viable yet. So in our work, we've been looking at single ion conductors, one type of solid polymer electrolyte. And we've come upon two types of ionomer structures that could be viable for faster ion transport. Now, the chemistries we've looked at in which we've found these interesting structures are not really viable as single ion conductors. They're based on carboxylic acid. But the concept of these morphology types, I think, is viable. And so what we're hoping to do within ACT3 with various partners, both from Giant and from Solvay, is to design chemistries that are amenable or that are likely to form these morphologies. So we have a morphology in mind, and now it's a matter of designing the molecules that will produce these morphologies. The most typical morphology in single ion conductors are discrete aggregates. So these are both atomistic molecular dynamics simulations, where the only thing that you're seeing is the charged entity, and the polymer chain is invisible in the rendering of the simulation results. So in this case, we have discrete isolated aggregates. This is not going to work so well for ion transport. But in this case, the whole golden color here, this orangey color, is one big aggregate. It is stringy, it is branched, and it's percolated the entire simulation box. This is a 6.5 nanometer simulation box. So this would be good as a percolated structure. You could imagine introducing a lithium at the top, and it could shuffle its way down inside these aggregates that are high dielectric constant. Another possibility would be these semi-crystalline materials that we found, where there is a crystalline domain and separated by these layers of acid groups. And so when we stretch in this direction, we can see there's two sets of scattering peaks. There's these low angle peaks and these high angle peaks. And that perpendicular orientation of those two scattering peaks indicates that we have polymer chains running this way and layers running this way. And these higher order peaks tell us that we really have layers. But the take-home message is both percolated structures and layered structures, ionic aggregates that form these two shapes, have more connectivity. The ions are more connected to one another, and that could facilitate ion transport. And now it's a matter of designing the molecules that will allow us to evaluate that. One of our fellows for ACT3 is Ted Trigg. And so he's doing some atomistic molecular dynamics simulations to look at these layered structures. We've proposed two different types of structures. This is an adjacent reentry. So this is one polymer chain pooled out of this pseudo liquid crystalline sort of structure, where it zigzags back and forth, dropping off the acid layers here that form these layers. Or we can have an extended chain. So we're looking at these two potential chain conformations for the layered structures. And we can evaluate which structure we have by comparing experimental X-ray scattering data with further calculations of what the scattering pattern would be as expected. Okay, and so the specific first project for TED is to look at not the sulfonic acids, not the carboxylic acids, but the sulfonic acids. We know they form layers. Over the weekend, Ted learned if they actually take up a good amount of water, which suggests a certain crystal structure. And so we're planning in situ EIS and X-ray scattering as a function of relative humidity and temperature. This can be done both here at Penn, and for faster time resolution, we can do this in Grenoble. Oh, and this was ERS as another characterization method. And to get a more detailed crystal structure, the nanofocus X-ray beam at EFRS within Grenoble is a fabulous opportunity to better understand these structures. So again, the collaboration with Grenoble is new for ACT3 and certainly new for my group, but there's a lot of opportunities. There's opportunities for in situ and in operando multi-scale characterization. This is critically important. There are opportunities to take these materials and actually build real batteries and evaluate them in real like a battery person would, not like a chemist would. No disrespect to anybody with that. They're just different sorts of skill sets, and this really allows us to look at battery materials in batteries, which is a huge opportunity. So with that, I will thank you and be happy to answer any questions.